All right, so last time we talked about average rate of speed versus instantaneous rate of speed. And we talked about how we're going to use the idea of average rate of speed to find instantaneous rate of speed, but with numbers that get closer and closer and closer to that time that we want. So we're going to talk about that. It's actually called a limit, and that's what we're going to talk about today. We're going to get closer and closer and closer to some numbers and use that to estimate limits. But first we have to talk about the definition of limit. Okay, I'll be straight up honest with you. It is wacko. No one likes the definition of limit. It sounds weird, but I think it's important that you hear it so that when you see it again, it won't be so crazy to you. All right, definition of limit. This is the mathematical definition. Assume f is defined near c, and let c and l be real numbers. Okay, this is not hard so far. We've got some function f, and we've got some value c, and the function is defined near c. It might have a hole at c, but near c, like for instance, right around here, near c, the function is defined. Okay, it is said that the function f has a limit of L as x approaches c. So as x is getting close to c, either way actually, okay, as x gets close to c, so as we're getting closer this way and as we're getting closer this way, that the function has a limit L if given any positive number epsilon, that's the Greek letter epsilon, there is a positive number delta, so that for every x, we have the absolute value of x minus the c. So wherever your x is and your c is, you're getting, remember, x is getting really close to c. So that delta is getting really small, okay? So whatever that value is, like if you're a little bit over here and you do x minus c, it'll be a little negative number, but if you're a little ways over here, that delta will be a little positive number because we'll do some bigger number x minus the c, which is smaller. So you'll have a little number delta, okay, and it's saying that the function, the whatever value of that x is right here, minus the function, or minus L, is less than some epsilon. Okay, it has to be a positive number, epsilon. That's why the absolute value. If we have that happening, if this number is getting smaller, this L that we don't know what it is, but that x that we're putting in near C minus that L is getting littler and littler, it's getting some positive little number, that is called the limit. That L number is called the limit. Okay, reality, nobody says that. Basically, they look at this little formula and say, all right, this little formula means the limit as x approaches c of some function f is L. We say, like I said, the limit of f of x as x approaches c is L. It's saying that as you get closer and closer to whatever value this is, c, your function value is getting closer and closer to L. It might not actually equal L, but it gets closer and closer to that. All right. So we're going to talk about some different ways to find limits during this entire chapter, but right now we're going to talk about a method of just trying some values and getting closer and closer and closer to the value we want. All right, so like for instance, this is a limit as x gets close to 1 of the function f of x. Well, let's look at f of x right now. If I put in 1, I get 1 cubed minus 1 over 1 minus 1. Well, what does that give you? 0 over 0. We have an issue. We cannot divide by 0. So we can't just figure out what the value of the function is at 1 and say, hey, the function has a value of 1. It doesn't exist. There is no value for the function at 1. So we're going to find the limit. We're going to find out not what the value is because there is no value. We're going to find out what it's getting closer and closer and closer to. So we're going to call that not the value of the function, but the limit as we get close to 1. So I wanted to graph this really quickly to see what this looks like. I did this on my graphing calculator. The graph will show up in a second here. right? It looks kind of like this, but when I traced, there was no value at x equals 1. Well, we already knew that because we're dividing by 0. There's no value in our domain at x equals 1. All right, so let's try things near 1. Well, 0.75 is pretty close to 1, so we're going to fill in this table down here. 0.75 is pretty close to 1, so let's actually go ahead and put in 0.75 to our function and figure out what the value of the function is near 1. So I want to do this quick calculation. So that value is 2.3125. All right, so let's try 1.25. That's also close to 1. It's equally as far away as 0.75. They're both 0.25 away. That is like the x that's close to c in the delta epsilon proof where we had, oops, sorry about that, 0 less than absolute value of x minus c is less than delta, and f of x minus L is less than epsilon. It's that x that's really close to our c. Our c in this problem is 1. We're getting close to c. And our delta then would be 0.25. We're 0.25 away on both sides, all right? So we're 0.5 more and we're 0.5 less. So let's go and do the 0.5 on the other side of 1 and figure out the value of the function. So that value is 3.8125. So we're not very close together. We're near 1, where our delta, our distance away from our value of x that we're looking for, 1, is only 0.25 on either side, but we're not getting a very good estimation for what the limit as we get close to 1 is. I'm sorry about that. So let's try doing something a little closer. Let's be 0.9, which is only 0.1 away from 1. So our delta now will be 0.1, a little better. Okay, so let's try x is 0.9 and see what our value is for the function. And let's do it on the other side too. So our delta is 0.1 and figure out what the values are. I want you to do that really quickly. I did it in my graphing calculator and used the trace function. So this is a little closer, 2.71 and 3.31. They're a little closer together, but they're not that close. I don't really know what the function is approaching. For my graph, it looks like it might be approaching something there. It's getting close, boogers. It's getting close to some value. I don't know what it is. My graph is a very rough sketch, so don't go by, oh, it looks like it's crossing at 3 there. It don't go by that. Or 3.2. Yeah, my graph is a very rough sketch. So let's get closer still. What if we made our x, we're going to be at 0.99 and 1.01. Then our delta, our change in x, is only 0.01. We're really only 0.01 away from our actual value, our limit that we're looking for. So calculate that. All right, so when our delta is 0.01, our values are 0.2971 and 0.30301. Now, those numbers are starting to get, notice that we're getting close together. I think we're getting close to 3. We're going to try one more delta of 0.001. We're going to try delta as 0.001, being only 0.001 away from 1. And we're going to find out the value of the function at 0.99 and 1.001. Both of those are 0.001 away from what our value of c is, our 1. So go ahead and calculate those. All right, so I got 2.997 and 3.003. Okay, so now we're getting pretty obvious that this is getting it's getting closer and closer and closer to 3. So is this, if we're looking from that direction, as we get closer and closer, as x gets closer and closer and closer to 1, as our delta, our little delta gets smaller and smaller and smaller and smaller, the value of the function is getting closer and closer and closer to 3. It never actually gets there. The function is not defined there because we're dividing by 0. There is a hole. It is at 3, right? We call this number the limit. Okay, as x goes to 1 of f of x, is 3. We're getting closer and closer and closer to 3. We never hit it, but we get really dang close. There's a hole there. The function is not defined. It does not have a value, but we're pretty sure that there's a hole right at 3. There are some algebraic ways to find this, and we're going to talk about that later on in the course. That's what we're aiming for, but for right now, we're going to estimate getting those deltas really small. Okay, so what about this epsilon? What is that? Well, our f of x minus that value that we are finding. So, like if we choose our f of x here, 2.997 minus our L that we think our limit is, that means that we have an epsilon of 0.003 because we take the absolute value of it. So that is less than some positive number, epsilon, whatever that number happens to be. Okay, as long as it's a positive number. So we're getting really close to our actual value. That epsilon is just kind of saying how close you are to the actual limit value. That is not the function value. And so that's how we're going to estimate. All right, so we're going to try one more. This time I did not fill in the table for you, but we're going to do it very similarly. We're going to find the limit as x goes towards 0 this time, so our c is 0, of that function x over the square root of x plus 1 minus 1 by finding of values of f near 0. All right, so let's just double check first that I can't just find the value of f at 0. So that would be 0 over square root of 0 plus 1 minus 1. Well, what do we get there? We have 0 over 1 minus 1 because the square root of 1 is 1. So we have 0 over 0. We cannot do that. This function right here, is undefined at 0. We can't just sub in and get a value like we have for many times in our mathematics careers, just found values that way. But there is no value. It's undefined. But what is the value of the function getting close to? We never get there. The function is undefined, but what are we getting close to? Right, so we need to pick some numbers, choose some numbers, values near 0. 0.1 is near 0. I'm going to put it over on the right because it is to the right of 0. And negative 0.1 is near 0, and that would mean our delta, our distance away from our c value, the value we're trying to get near, is 0.1. So let's go ahead and calculate those. This is not the correct necessarily way to choose it first. I chose that. You could have chosen 0.25, I guess, but I'm going to get closer rather than further sooner. So I got 2.04-ish and negative 0.94-ish. So those are my first two. Now, they're not real close together. Oftentimes they'll say, find a value that is your epsilon is less than 0.0001 or something. Basically, they're saying make sure that your limit and the values that you're finding you get close enough to estimate by 0.001. Be within 4 decimal places correct before you say, I think I'm good. So we're not. They might say 2 decimal places, but I'm going to say 4 for this one. So now let's do a delta of 0.01 then. So I'm going to do negative 0.01 and 0.01. I see I have an extra column over on this side, so we're going to not need one of those boxes. All right, so go ahead and calculate those. So I'm pretty sure now that my limit, that I am getting close to 2. Even though the function's not defined, I'm pretty close to 2. But like I said, I want my epsilon to be close within 4 decimal places accuracy. Right now, my epsilon, I think that my value of my function is 2. I'm going to do it this way. And we're going to subtract the values that we're getting, 2.0049. My epsilon then, I'm going to erase a little bit. I get 0.0049 is less than my epsilon. That's not close enough. We're not within 0.001. So we keep going. Let's try 0.001. So our delta, our little d delta, is 0.001. So we'll do 0.001 on that side, and let's see if I'm close enough. So now let's look at my epsilon. I have 2 minus 2.0004. The absolute value of that is 0.0004. We are not good enough yet. So we need to go ahead and do one more. So let's do 0.00001 as our delta. And let's see what we've got. I don't have room on the other side, so I'm not going to do that side. All right, so now we are within the right distance. Our epsilon is definitely less than 0.001. We're at 0.00005. So we definitely know that we're at 2. We've got our guesstimation within that, but our L is 2. Our limit is 2. I didn't actually graph this on the picture here. It kind of looks like this if you were following on it. I used my trace function to find these values, so I did graph this right away. If you graph and trace at 0, there is no value because 0 divided by 0, we don't have a value. But I used my trace functions as a way to calculate quickly all of these values. Otherwise, these problems are extremely tedious to substitute every single number in. So that is a hint to you to try to do these. All right. Next up, we're going to try to talk about when limits exist and when they don't. We're also going to talk about what we do to analytically find these limits rather than getting closer and closer numbers and guesstimating what the limit will be. Because right now that's really what we're doing, is we're guesstimating what the limit will be. So until next time, there we go.